Welcome to the lesson on sensors. We have talked extensively about the control loop, and in the last two lessons we have focused in on the controllers and a couple of the more common control devices, the control valves and dampers. This lesson will take a deeper look at another component of the control loop, the sensor. Sensors are used to measure some property. It could be temperature, pressure, flow rate, or a host of other things. Sensors come in a variety of different types that utilize a lot of different technologies in an effort to accurately measure the property in question. The intent of this lesson is to define some of the characteristics of sensors. We also provide a how it works description for some of the more common sensors encountered in HVAC systems. We do have to be careful here. We don't want to unleash too many cans of worms in this lesson. Just like the control valves and dampers lesson, a lesson on sensors could easily be turned into a class in and of itself. There are just too many sensor configurations and technologies available for use in HVAC systems for us to be able to talk about all of them. And you don't have to be an expert in sensors to be able to understand how HVAC systems are to be controlled. But we do feel that a quick explanation on some of those technologies will help you feel more comfortable with the topic. If you want more on sensors, Chapter 4 of the Montgomery and McDowell text is a good starting point, but I'm sure you could find additional textbooks out there that dive even deeper into the subject. The objective for this lesson will be for students to comprehend the functions of sensors and the obstacles they face in trying to carry out those functions. The corresponding samples of behavior will be: state the functions sensors perform in an HVAC control system, explain the difference between accuracy and precision, describe when a sensor would require an accompanying transmitter, recall the selection criteria for sensors, summarize why relative humidity is not the most appropriate measure of humidity, and discuss why the use of passive flow sensors can benefit the energy performance of a system. What are sensors used for? As I just stated, the sensor is a component of the control loop. It doesn't matter if that control loop is an open or closed loop. Both types would contain a sensor. Sensors located in the control loop need to not only be able to measure the property they are looking at, for example, the temperature of an airstream or the pressure in a hydronic system, but they also need to transmit that information back to the controller. As we get into some of the more common styles of sensors in this lesson, it will become obvious based off how the sensor works that information is not always packaged in a format that can be sent to the controller located 10, 20, or even hundreds of feet away. For instance, the output signal of a board-on-tube pressure gauge may be the position of a mechanical linkage. That position needs to be converted into a more usable format in order to transmit that information to the controller. That required format of the sense variable signal is often a voltage for electronic and digital control systems, or in the form of air pressure for pneumatic systems. If the configuration of the sensor doesn't directly produce an output signal in the required format the controller needs in order to accept it, a device called a transmitter is required. Again, the transmitter converts the output signal of the sensor into an output signal in a format that can be sent to the controller. Often the sensors and transmitter are going to be packaged together, and differentiating between these two functions may not be necessary. But we wanted to provide you with all the terms required for you to speak the language of controls to others in the industry. Sensors need not always be part of an automated control loop, however. HVAC systems often have sensors located throughout them for monitoring purposes. Just walk into the nearest mechanical room. You will probably see a few pressure and temperature gauges located throughout the duct and piping systems. The sensors connected to such gauges are not often being used for additional purposes. They are just providing a status of the system to those who read them. So we have sensors for two functions. First, to provide information to a controller, which will in turn make a decision on how to control the system. And two, to offer monitoring of the system's operation. But what are the properties being sensed in an HVAC system? There are many. The most common would be temperature sensors. They are used throughout an HVAC system. They can measure the room temperature, as that is a good indication of thermal comfort for occupants. They can measure the temperature of air coming off a heating or cooling coil. They can also measure water temperature leaving a boiler or chiller in an effort to keep them at a prescribed set point. These are just a few examples. Carbon monoxide sensors are often present for life safety concerns. They are needed when some sort of combustion process is being performed. Theoretically, the natural gas furnace in my house is burning clean enough so that no carbon monoxide is being produced. If carbon monoxide is produced, hopefully it is all exhausted out of the flue. But just in case carbon monoxide is produced, and it somehow gets into the occupied space, I have a carbon monoxide sensor which will trigger an alarm to alert my family if carbon monoxide is present. Carbon dioxide, or CO2, is not quite as harmful to us humans, but it is a good indicator of indoor air quality. Thus, CO2 is at times measured in an HVAC system to allow for control of how much outside air should be brought in to meet ventilation requirements for the occupants. Such a control strategy is called demand control ventilation. Other property measurements can be performed to determine indoor air quality, such as ozone or volatile organic compounds, or VOC sensors. However, these are not as common and will not be discussed in this course. Smoke sensors are also used for life safety purposes. When the presence of smoke is identified, a signal is usually sent to initiate an alarm to alert occupants. Additionally, such a presence of smoke in the ductwork system could be used to initiate a control sequence in the air handling system to allow for safe exit of occupants, for starving the fire of oxygen, or at a minimum, just shutting down the system to prevent the spread of smoke to other locations in the building. Controlling for humidity levels in an airspace is not always done directly, but there are times when it is. In such instances, humidity sensors are required. They can come in the forms of relative humidity sensors or dew point temperature sensors. The difference between these two properties and why dew point temperature sensors are preferred will be discussed later in this lesson. Pressure of an airstream, pressure of the water in a piping system, or a difference in pressure between two adjacent air volumes is often measured and controlled for in HVAC systems. Differential pressure sensors between supply and return piping are often used to control the speed of pumps. Static pressure sensors located in supply ductwork is similarly used to control fans in variable speed operations. And lastly, flow sensors can be used in a variety of ways. For one, they can be used for metering purposes, such as how much natural gas, steam, or chilled water from a centralized generation system is entering the building. They can also be used to prove flow. For instance, it can be damaging to the evaporator in a chiller to operate the chiller without having water flowing through it. Ice could form around the evaporator coil, refrigerant pressure could drop, and a host of harmful consequences occur when this happens. Sending a command to the chilled water pump to turn on isn't enough to ensure flow is occurring. Thus, we often have a sensor in the pipe to independently verify that flow is occurring prior to sending the command for the chiller to turn on. Lastly, there are times when the flow of a fluid is actually the control variable in a closed control loop, as is the case for pressure-independent VAV boxes and control valves. The various examples of the control loops, which include measurement of these different properties, will not be elaborated on much more in this lesson, but I assure you each such control loop will be discussed in detail in Module 2 of this course. For instance, we will not be talking about actions a controller would take if measured CO2 concentrations get too high. Discussion of that particular control loop will be discussed in the ventilation session of Module 2. The remainder of this lesson will focus on how the various sensors themselves take such measurements. But first, we need to define some of the performance characteristics that are often used to quantify the performance on various sensors. Let's start with this concept of accuracy. The Montgomery text defines accuracy as the conformity of an indicated value to an accepted standard value. This is just a measure of how true the sensor's reading really is. Each sensor is manufactured in a way to maintain a certain level of accuracy over a certain range of the measured variable. For instance, a relative humidity sensor may provide readings with an accuracy of plus or minus 5%, but only if the relative humidity of the airstream is between 20 to 80%. Anything reading close to or below 20%, or close to or above 80% can't really be trusted. Thus, the concept of range is an important factor when selecting a sensor for the application you are using it for. The concept of range is formally defined by the Montgomery text as the difference between the highest and lowest operational values. And then we have resolution. That is, the ability of the sensor to detect changes in value of the measured variable. If accuracy is considered, without considering the range and resolution of the sensor, the measurement objective may not be satisfied. Then there are two terms that effectively mean the same thing. They are repeatability and precision. The Montgomery text defines them as the closeness of agreement among repeated measurements of the same variable under the same conditions. That's a mouthful, so let's provide an example. Say the temperature of a space is 75 degrees Fahrenheit. You bring the sensor into the space and it outputs 78. You leave the space, come back in again, and the sensor again states 78. Say you do this over and over again, each time with the same result. Well, 78 degrees Fahrenheit is not 75 degrees Fahrenheit, so the sensor is not accurate per se, but the outputted values from the sensor that come from measuring the same value are all the same. Thus, the sensor is said to be precise. This may be counter to what you had previously thought precise meant, but I assure you this is how they define it in the controls industry. Let's take one more look at the difference between accuracy and precision, because that is one thing that can hang people up. Here is a plot which shows the output readings from two separate sensors. The dotted line is the actual temperature that is being read. One sensor's outputs hover very close to the actual temperature of the space. Thus, it is said to be accurate. But the readings do bounce around a bit. Thus, it is not too precise. Just the opposite is true for the other sensor. It maintains a pretty constant offset in its output compared to the actual temperature. Thus, this sensor is precise. But since there is an offset, this sensor is not accurate. Take a minute to let this all digest. Lastly, we have reliability. Obviously, we would like a sensor to be installed that will be reliable for an extended period of time. That is, it will continue to provide repeatable and accurate results over a specified period of time, as it did when it was first installed or calibrated. One way to quantify how reliable a sensor is through the concept of drift. For instance, a temperature sensor manufacturer may state that their sensor has a guaranteed maximum drift of 0.5 degrees Fahrenheit over the course of 5 years. This means that for the same temperature being measured, the sensor output now and 5 years from now will be no more than 0.5 degrees Fahrenheit different. So even if that is the case, how much are we going to trust that sensor's measurement at some date after this? Sensors need to be calibrated on a regular basis. This is often a neglected preventative maintenance task, but it is required. The Air Force's preventative maintenance task listing has been made available to you. As you look through it, you will see sensors and air handling units and primary equipment, such as boilers, chillers, and cooling towers, require at least annual verification their sensors are functioning correctly, and if they are found not to be, calibration or replacement must take place. To sum it up, there are many factors that go into how well a sensor will perform. Basically, you want the most accurate and precise sensor, with the appropriate amount of resolution your budget allows for. But you also need to consider range, reliability, durability, maintenance requirements, and compatibility. The concept of compatibility has two elements to it. Interchangeability is defined by the Montgomery text as the ability to physically replace a sensor from one manufacturer with a sensor from another, and have them read the same values. Interoperability means the output of the replacement sensor is in a format that can communicate with the connected controller. The rest of this lesson is just going to identify some of the more common sensors out there and provide you a how it works tutorial on a few of them. Let's start with the temperature sensors. One of the most common types of temperature sensors is that of the bimetal or bimetallic strip. This is just a strip of two different metals bonded together. The metals have different thermal coefficients of expansion. That is, when heated, they expand at different rates. If the strip is heated, the side with the metal with the higher coefficient of expansion will expand more, and subsequently it will bend over the top of the other strip. This strip could be positioned in a way so that at a prescribed temperature, the strip will reach a contact to complete an electrical circuit. Or it could be positioned in a way to open or close over an orifice to allow more or less air in a pneumatic control system to be sent to a controller. The idea of using metals with different coefficients of thermal expansion is captured in several other types of sensors out there, to include the mercury switch as well as rod and tube sensors. Thermocouples make use of what is known as the Seebeck effect. Basically, if you have a metal conductor exposed to two separate temperatures, a voltage difference between the two ends will develop. The extent to what that voltage difference is will depend on the metal used in the conductor. A thermocouple joins two dissimilar metal conductors on one end. That junction is placed in a location where the temperature is being measured. The other unjoined ends are brought in contact with the location of known temperature, and the voltage difference between these ends is measured. Based off the voltage read, the temperature difference between the location being measured and the reference temperature can be determined. The issue here lies with having to know what the reference temperature is, to be able to know what the temperature you are measuring is. Thus, thermocouples are typically only used in high temperature measures, such as in hot water systems or flue gas stack coming out of a boiler or furnace, where the reference temperature can be assumed to be a prescribed room temperature, where relatively small deviations in reference temperature will not provide drastic error in the measurement. There are several types of temperature sensors that make use of the fact that some devices can have a change in their electrical resistance when they are operating at different temperatures. Sending a current through such resistors and measuring the resultant voltage change can be used as an indicator of what temperature the resistor must be exposed to. Thermistors, resistance temperature detectors, and integrated circuit temperature sensors are all technologies which make use of this phenomenon. Going into much more discussion on how these devices work would require us to revisit several electrical concepts. In the interest of time, we will instead encourage you to look into these various types as you see fit. Smoke sensors typically utilize one of two technologies. The first is photoelectric smoke detectors. Photoelectric type sensors aim a light source into a sensing chamber at an angle away from the sensor. When smoke enters the chamber, light is reflected onto the light sensor, triggering an alarm and possibly sending a command to the air handling system to initiate a smoke control sequence. These sensors are sensitive to larger size particles and are typically installed in the exhaust or return ductwork of an air system. Ionization type smoke sensors can detect smaller particle sizes and are more appropriately used in the supply ductwork of an air system, since the majority of large particles would have been already removed by the filters at the air handling unit. These type of sensors have a small amount of radioactive material between two electrically charged plates, which ionizes the air and causes current to flow between the plates. When smoke enters the chamber, it disrupts the flow of ions, thus reducing the flow of current and activating the alarm. As I stated before, there are several parameters that can be used to quantify moisture or humidity in the air. Now I am going to assume you all have been exposed to the psychrometric chart, because that is where I'm going with this. If you have not seen what I am about to show you, or you need a refresher, please take a few minutes to watch the lesson from Introduction to Mechanical Systems on this topic. That lesson is located in the additional references we provided. Looking at the psychrometric chart, we have dry bulb temperature running across the horizontal axis. We have humidity ratio, which is really an absolute measure of humidity content in the air, located along the vertical axis on the right-hand side. We also have these lines that look like ski jumps going up and to the right. Those lines are the relative humidity lines. Relative humidity is defined as the ratio of water vapor in the air to the amount of water that air can hold at the same temperature and pressure. Keep in mind this is a relative reading. For instance, say we have air at 75 degrees Fahrenheit and 50% relative humidity. If we heat that air without removing or adding moisture to 90 degrees Fahrenheit, what happened to the relative humidity? It went down to somewhere in the low 30% range. Even though it is the same air with the same amount of moisture in it, the relative humidity will change as it is dependent on the temperature of the air. But what doesn't change? The humidity ratio, as measured on the right-hand vertical axis, didn't change since the amount of moisture in the air didn't change. Again, we said that this is the absolute measurement of humidity. The dew point temperature also didn't change. Though the dew point is taken from the 100% relative humidity line, a quick investigation in the psychrometric chart provides that this value too is a measurement used to indicate the absolute amount of moisture in an air volume. Since relative humidity is dependent on temperature, it is usually better to measure for an absolute value of humidity, like that of humidity ratio or dew point temperature, when trying to control our humidity levels in an HVAC process. Nevertheless, there are relative humidity sensors out there. Some such sensors make use of the fact that there are materials that expand and contract when exposed to air of differing relative humidity levels. The change in dimension of such materials could then be used to estimate the relative humidity of the air they are exposed to. Such materials include animal hair, wood, and various natural and synthetic fabrics. There are also some hygroscopic materials whose electrical resistance increases and decreases with changes in relative humidity. This is very similar to the effect we saw in temperature sensors when the electrical resistance of a material changed with changes in temperature. Just like those temperature sensors, these types of relative humidity sensors can be used to predict the relative humidity of the air they are exposed to based off of the electrical resistance they are exhibiting in an electric circuit. There are other types of relative humidity sensors, such as the Jason type capacitance sensor, which can provide very accurate readings and are quickly becoming the norm in HVAC control systems that use relative humidity sensors. As we said before, relative humidity is not the best measurement due to its dependence on air temperature. Thus, it is better to measure either humidity ratio or dew point temperature, both of which are absolute measurements of the quantity of moisture in the air.